All right. I guess let's get started. Um, it's an honor for us today to have Dr. Hatem Ltaief for us as a keynote for today in this seventh edition of the KAUST NVIDIA workshop on accelerating scientific applications using GPU, an effort that we've been conducting with NVIDIA for several years now. And today we welcome Hatem Ltaief. He is a principal research engineer, research scientist at the Extreme Computing Research Center at KAUST, where he's also advising several master's and PhD students for research. He received his engineering degree at Polytech Lyon at the University Claude Bernard Lyon in 2003, master's in applied mathematics in 2004, and PhD in computer science in 2008 at the University of Houston. Prior to joining KAUST, he held the position of a research scientist position at the Innovative Computing Lab in Knoxville, Tennessee, in the US. His research interests include, but not limited to, parallel computing, numerical algorithms, parallel programming models, performance optimizations for manycore architectures, and high-performance computing in general. He has contributed to the integration of numerical algorithm into mainstream vendor-specific and scientific library, numerical ones mostly, such as the NVIDIA cuBLAS, which is the most relevant for today, and CRALIPSci as well. He has been collaborating with domain scientists, astronomers, statisticians, computational chemists, geophysicists, on leveraging their applications to meet the challenge at Exascale. It is also noting that Hatem is the founder of this workshop itself, being the chair of the first edition of it back in 2012. And he is now coming back again to contribute, and actually he gives contributions every year on different forms and help us either during the hackathon with his team or various inputs to us in this workshop. So thanks, Hatem, for joining today, and we are looking forward to your talk entitled GPU Accelerated Applications, the Why and the How.
Thank you, Sabr, for the nice introduction. It seems to be as long, perhaps, as my talk. Hopefully not, but we'll find out. Appreciate it. It's a really great pleasure as well to be here to present you some of the work we've been conducting in the center, Extreme Computing Research Center, led by David Keys at KAUST. So before I proceed with the technical content, I really would like to acknowledge the work done by several people in our center, from student, postdoc, research scientists, and collaborators, as well as the supercomputing lab team at KAUST. We have also several collaborators in France, people from INRIA Bordeaux in the US, from my previous employer in Germany, Lebanon, and also a whole gang, if I call them gang, of astronomers from Paris Observatory, from the National Astronomical Observatory of Japan, as well as from the Research School of Astronomy and Astrophysics at ANU in Australia. And some of, actually most of the collaborators that I mentioned here, they are mostly from domain science, and we put together projects, multidisciplinary project to try to take their workload, day-to-day workload to advanced hardware architectures. Of course, vendors. We at the center, we have the NVIDIA GPU Research Center, so we have a close collaboration with NVIDIA, and this goes back almost 10 years ago. We have also collaboration with Intel, with Cray, and also active collaboration with ARM and NEC. So the size of the logo here tells you how much support we're getting from those vendors. All right. It's difficult for me to talk about an HPC, or to give an HPC talk without really looking at this top 500 list. Not because it gives fancy numbers to run a naive benchmark that saturate the the floating point units and give you a huge number in terms of performance, and then ranks you on this list. but rather to look at the technology, right? To look at what is the technology, the underlying technology, hardware technology that takes you to that, extreme parallelism, because, that technology is important to be acquainted with to make sure, your workload works well and effectively on those hardware. Number one today is Fugaku, is a system hosted in Japan. It's a non-GPU system, although it behaves like a GPU, to be honest with you, for several reasons that I will skip for the time being. But if you look at the top 10, I believe the five, you have 5 systems that are powered by NVIDIA GPUs, and this of course shows the huge impact that the NVIDIA technology had on developing new hardware architectures. Just in case you are wondering what's beyond ExaFlops, we have plenty of performance waiting for us, as long as we know how to use them appropriately. And I hope my talk today will show some of the ingredients necessary to do that. So one thing that was really striking for library developers is to look at this 42 years chart of microprocessor trend data. Okay, so we're looking at the years basically in the x-axis. In the y-axis, we're looking at various various ingredients in your hardware, going from transistors, going to single-thread performance, looking at frequency, typical power consumption, and the number of logical cores. So this chart is actually from 2018, and it's not really up to date, but the trend is there. The trend goes as follows. When it comes to power, frequency, and single-thread performance, we reach a plateau there. Okay, so if you used to enjoy high frequency every time you have a new processor coming up, this is done. You cannot really enjoy that anymore. If you look at single-thread performance, because it's linked also with the frequency, we also reach that limit. Okay. If you look also at power consumption, all those three actually really interrelated to each other. We also reach a plateau there. So when it comes to what is really evolving yet is the number of logical cores. Okay, the number of logical cores. So this tells you that we have now, architectures with extreme parallelism under the hood. Okay, so it becomes, of course, important for algorithm developer or library developer to take this into account and make sure to expose parallelism in their algorithm as much as possible. The other trend to look at is the number of transistors. Okay, in that chart, it sounds like it keeps increasing, right? So, but if you look at the latest chart after 2020 and beyond, from John Chalf, he put it together. You actually also start seeing the number of transistors plateauing. Okay, so this is yet a post-Moore law that we have to, as a community, handle properly. And this takes us to mostly solution based on heterogeneous hardware computing. And this is where, this graph shows basically the foundation, or gives the context of my talk. My next slide shows another point to also highlight when looking at the memory technology scaling, looking at the energy perspective in terms of how much energy does it take to compute at the level of the registers, and comparing this with how much energy it costs to move the data off chip. Okay, so there is at least 1 to 2 order of magnitude in terms of energy consumption. And this again tells you that you really want to make sure you avoid moving data around. As soon as you load up your data to do computation on it, you really want to make sure you again try to reuse it as much as possible before shipping it off to a remote system that may also need it to do calculation on. And this takes me to this cartoon showing some of the, I believe, HPC ingredient, or the ingredient for this HPC recipe for exascale computing that I have already mentioned some of them in terms of reducing data motion, removing synchronization point. You can't afford to have millions of threads to synchronize at a rendezvous point to exchange data. You have really to alleviate that bottleneck. We're looking also at fine-grained parallelism. So again, to expose parallelism so that you could run on multiple threads. Power efficiency, this is something that also is of extreme importance. And this is something we are also looking at. We also believe in user productivity, okay? So we believe a lot in user productivity in terms of how much effort it takes to take an existing code for a given platform to embrace a new architecture, even from the same vendor or even from another vendor. Okay, so we really try to avoid or abstract, the hardware complexity, and to that end we use dynamic runtime system. We really abstract the processing unit, whether it's a GPU or CPU or any processing unit you have there. We try to abstract it by using runtime systems and basically giving this hot potato in terms of orchestrating the various tasks on various processing units. We give that hot potato to runtime systems. So it's another community that we work with closely, and so that we have sort of those two swim lanes, and where people work and focus on the algorithm part, trying to expose parallelism as much as possible. And then people who would then look at your various tasks and try to run them and schedule them in an efficient way so that, you can reach, you can extract high performance from your hardware. And I believe this is some of the recipe that not only applies for numerical libraries, but apply across the board for, it's apply for, application for various algorithms out there. And, it's important to cover those bases. So this is a chart that I put together, actually a few months ago at a conference on computational astronomy. It shows some of the hardware trends and some of the algorithmic trends. Okay, so it's sort of a pie chart. And the idea that I wanted to convey here in this cartoon is, those two swim lanes between the hardware, and how the technology scaling taking us at huge performance improvement within just 5 to 7 years, and looking also at the development in terms of algorithm on the right side. So, and to get the maximum benefit out of hardware, and you need to have the proper algorithm for it. But also, if you want to maximize the performance of a given algorithm, you need to have the proper hardware for it, right? So, it's what comes first, the algorithm or the hardware, right? So it sounds a bit like a chicken and egg, problem, but when you think about it, I think it's a great opportunity for synergism here, or co-design between development on the algorithm front and the hardware technology. And this is something that we try to really focus on in our center. And one of the idea that we try to leverage is what we call matricization. For several reasons, we want to do this. So the idea is that you have an algorithm, a numerical algorithm, you want to really try to matricize as much as you can. So the reason why is of course, because of the hardware trends, right? So you have now the development of, hardware technologies that do fast math, computation with hardware support. And, this is important for the development on algorithm, to do that. Also, matricization is important on the development, side of the algorithm, for portability, for performance portability. Today, let's say we run on Intel. Tomorrow, we may run on AMD or NVIDIA or any, architecture, fancy architecture that is out there and show, promises in terms of performance. By really matricizing your problem, you rely on an abstraction of those matrix operation called BLAS, basic linear algebra subroutine. And those BLAS comes for free optimized by the vendor. So every vendor, anytime they come up with a new architecture, they will provide you an extremely optimized BLAS implementation. So if you come with your algorithm and your algorithm is expressed in terms of those basic matrix operation, you basically off the hook when it comes to porting your application or numerical algorithm on that hardware, because the legwork would be made by the vendors. It's critical for them to make sure those BLAS routine work as fast as possible on their hardware. So by us taking this or embracing those BLAS routine into our algorithm, we are really able to run on various instruction set and various architecture. And this is, I think, a path moving forward that is important to highlight. And of course, we try to tell the domain scientist people we work with that this is an important path also to take. Since money funding towards software is usually limited, therefore one cannot really afford to hire an army of postdocs to port several application and codes to a new architecture. And I'm not saying all application and algorithm can be matricized, but whenever there is this opportunity, I think it's important to embrace it. Okay. I'm not sure how much I'm doing in terms of time, but hopefully I'm getting okay. So this is the library that we work on. Okay, this is HICMA, stands for hierarchical computation on many core architecture. I'll be talking about it a lot during this presentation, but I just wanted to put this chart here right now so that you know that the work that we are doing is in this context, in the context of HICMA. Okay. All right. And of course, I'd like to put one slide here about Shaheen. Shaheen is our supercomputer at KAUST, as you all may know. It's number 52 in the last November top 500 list. It's time to get refreshed, and my colleague at KSL are leading the work there, and we are really excited about it, and we're looking forward to getting refreshed within few months. Okay, so the work that we are doing at ECRC, we try really to work with domain scientists, because we firmly believe that we may optimize a given matrix operation, but we may leave lots of low-hanging fruit out there if we don't team up with domain scientists, right? By teaming up with domain scientists, we do realize that there are lots of opportunity to further improving performance, okay, to further customize some of our numerical libraries and algorithm to support a given domain science. And there are some of them here that I'm going to list. So basically, in material science, we have a huge group of faculty members at KAUST working on designing new material that require studying the electronic structure of various molecules. We have also a large group of faculty working on seismic imaging in earth science, trying to X-ray the subsurface and finding out oil and to help extracting the oil. And this basically consists in solving this acoustic wave equation. We have also a lot of computational statistics people working on climate weather forecasting. And the idea is to optimize this maximum likelihood estimation, where if you see the sigma here, the sigma is as large as the number of observation. So you are looking at putting sensors in a given region on Earth and try to record, it could be wind speed, soil moisture, temperature, whatever parameter you are interested in. And that matrix is as large as the number of observation. And that matrix, therefore, could be really of size of million or even billion if you were to take all the data registered by the satellite. Okay, and the other application we are also focusing on in our center is the work done by computational astronomers using ground-based telescopes. There are several efforts in ground-based telescope at this point in time, and perhaps the most advanced one is this European Extremely Large Telescope. This is the largest ever built telescope that will be deployed in a few years in Chile. Again, the astronomers using those telescopes, they're trying to find habitable exoplanet. It's like Earth is not enough for us anymore, I guess. When you look at all those applications, right? When you look at those 4 applications that I mentioned, you know, we look at them as we try to identify. I mean, you know, a common, common workload. What could be the common workload for those 4 applications? And you know, we try to look at those several applications that we would like to support, and we want to deploy them on several architecture. So when it comes to deploying them on several architecture, I mentioned already the matricization, the importance of matricization, right? Of expressing your algorithm in terms of BLAS. And that's how, you know, today we are able to deploy our, various algorithm on various vendors. Okay, and when it comes to those various applications, we also identify a common denominator. Okay, we identify a common denominator, and this is how basically ECRC is able to tackle several applications and to deploy them on several architecture. That common infrastructure in those particular applications, the name of that algorithm is this highly ranked guy, André-Louis Cholesky. He's a French military. He passed away a long time ago, of course, and actually very young, at a very young age, but he gave us this cool algorithm, this Cholesky factorization, right? So this Cholesky factorization is one of the most time-consuming operation in those 4 applications that I mentioned, okay? And the idea of this Cholesky factorization, it takes a dense symmetric positive definite matrix and try to factorize it. So by factorizing it, then I can solve my maximum likelihood estimation. I can solve my Schrödinger equation for material science. I can solve the pseudo-inverse or the tomographic reconstructor for the computational astronomy, and so on and so forth. So once we identify that critical matrix factorization, we try to see how we could optimize it. Okay, if you use last century technology from LAPACK and ScaLAPACK libraries, and look at how Cholesky factorization is being done, there are lots of issues with the inherent algorithm. The algorithm is called block algorithm, and the idea is that you do some blocking within this panel factorization. So that's my matrix. That's my gigantic matrix that is dense. And what I do, I split it into panels, and I try and I accumulate some of the operation here so that I can apply them during the trailing submatrix, doing an update based on level 3 BLAS. Level 3 BLAS are those BLAS that are rich in terms of arithmetic intensity. They are GEM, basically. They are matrix multiplication. So this is where most of the performance is being extracted. So you block here your operation, and then you apply them at once using fast implementation of matrix multiplication. So the problem with this those implementation here is your panel is mostly memory bound. Your panel is basically gets saturated within few number of cores in your system, because it's mostly bound by the speed at which those cores are able to bring the data from main memory to registers. Okay, therefore you have a slow phase and rather sequential phase called the panel. Once that panel is done, then you can unleash all your power and do your matrix multiplication. And then you can move to your subsequent steps until your whole matrix is factorized. The problem with this approach is that you have in between those phases synchronization point. You have point where all the threads have to synchronize before moving to the next subsequent operation. And this is of course a no deal. Okay, this is of course not possible to do such approach. And we demonstrated already that on many core architecture, with lots of parallelism being exposed, this approach does not scale. We've seen then from this century a new implementation in those libraries, Plasma, MAGMA, CHAMELEON, SLATE, implementation of this Cholesky factorization on many core architecture. And this works rather great. It uses tile algorithm, and tile algorithm consists in taking your whole matrix. You don't split it into panel as before with LAPACK, but rather you split it into tiles, into small, tiny guys, tiny blocks. And the data in those blocks are now contiguous in memory. And you basically split your algorithm. So you expose parallelism here in your Cholesky factorization so that all those operations can then proceed in parallel. Okay, so you don't have to wait until your whole panel is done to start working on your update. Things happen in really more asynchronous way, and performance demonstrate that those libraries are able to extract are able to achieve huge performance speed up compared to LAPACK and ScaLAPACK on many core architecture. So that was the trend in the first, I would say, or the end of the first decade in 2000, 2007, 2012, where we've seen lots of implementation based on tile algorithm in those numerical linear algebra libraries, and performance was able to, of course, get a huge boost. But we reach an end of it, all right? I mean, an end in the sense that to support those applications that I mentioned, those matrices actually are gigantic, could be of order of billion matrix size if you have billion geospatial, for instance, location to record temperature on. Okay, and of course handling this in a dense matrix on today's supercomputer, you don't have enough memory at all to store such matrix. Okay, so it's not possible to proceed or to solve such problem with this application. Okay, but the low rankness property of those matrices come to the rescue. Okay, the idea is to exploit the low rankness of these matrices. If you look at those matrices, although they are apparently dense matrices, they are data sparse. They have sparsity not in the structure but in the data. Okay, the data that the matrix contain has sparsity in it. So could be because of redundancy. It could be of for various reasons, right? And then what you need to do here is to try to see if you could take advantage of that data sparsity and then see if you can compress those matrices. And this is all what HICMA is all about. Okay, so HICMA is a dense linear algebra renaissance in the sense that we are pushing the limit of the existing dense linear algebra libraries that I mentioned before. We're pushing the limit in the sense that we are trying now to solve even larger problems that could not fit in memory on today's supercomputer. And the idea that we take for that is we compress those tiny tiles here, those tiny blocks of my dense matrix. We compress it, right? So then we end up having blocks outside of the main diagonal that are represented by this new data format or new data compression format that result from doing a singular value decomposition, SVD, or any actually other compression method could be employed here, as long as you capture the most significant information or data out of this block. So you went from a dense tile to a tile that is represented by those two UNV matrices or tall and skinny matrices, that if you were to perform the outer product of those two, you would go back to the dense representation. Of course, we do not want to go back to the dense representation because we are interested in solving large problem. Okay, so this tile low rank, this is how we call it, tile low rank data format, is not new. It has been done by by two theses in France, and our contribution here is really looking at this tile low rank format as a pragmatic approach. Okay, there are much more advanced out there data compression format. We decided to start with this compression format because it would allow us to build on all the expertise we developed during the last decade or so in developing linear algebra, advanced HPC linear algebra. And so this is how this is really I would say the DNA of HICMA, is to compress. And then once we compress, we need to do factorization on the compressed format. And again, this is what HICMA is all about. I'm recalling here this chart. So of HICMA and its software stack. So it has various software stacks. And this is the gray area BLAS. So the gray area is basically those external dependencies that would come available on a given system. And BLAS give you basically the performance boost. Okay, so we rely on BLAST, as I said. We rely on BLAST to get performance. And the red boxes are the boxes that come with HICMA, with HICMA distribution. So we have our own BLAST. Okay, we have our own BLAST because for some of the BLAST operation that we are after, or that HICMA relies on, it turns out that the vendor sometimes do not do a great job in getting performance. So we do implement a subset of those BLASTs, and some of those implementation actually then ended up into the vendor numerical libraries. So this is a great contribution that we are looking after. We have also other boxes here. StarsH is a library that generates the compressed matrix from a given matrix kernel. HCore contain the monolithic sequential kernels that the HICMA drivers will operate on. One piece here of a box that is really important for us, if you recall from my HPC recipe, is those dynamic runtime system. So HICMA, the driver of HICMA when it comes to doing Cholesky factorization, it will call those runtime systems to orchestrate the various HCore routine and try to monitor the data dependencies and schedule the various tasks onto underlying processing units. So that's what HICMA is all about. Oops. Oh, apologize. Let me go back to here. All right. So I'll give you an example here. Okay. So, and this is taken from our colleague from computational statistics in handling this geospatial statistic application in 3D. This is my matrix. This is a matrix, and it has 10 tile by 10 tile, and each of those 10 tile have size 250 by 250. What I do is, and I do an SVD on those off-diagonal blocks. And when I do an SVD on those, or compression on those blocks, the number that you see here is the most significant number of singular values that needs to be retained to give you an accuracy at the end of 10 to the power minus 8. So we went from a 250 by 250 block size, dense block size, to retaining only 27 singular values. So there is a tremendous gain here in terms of memory footprint, obviously, right? You require less data to be stored, but also in terms of arithmetic complexity, you do less computation, right? So it's like one stone, two birds. You are able to solve not only large problems, but also solve them rather fast. And this is HICMA on Intel architecture. I know this is an NVIDIA workshop, but I'm showing Intel results so that I can then highlight the NVIDIA impact on HICMA. So this is looking at time to solution in y-axis and matrix size in x-axis, right? So the lower, the better. We are looking at basically various hardware technology, various Intel technology, going from Sandy Bridge to Haswell to Skylake. And we're also looking at various algorithm implementation. So the dense implementation, right? The dense implementation is the implementation that do not do any compression. We'll just take the matrix as is and in a brute force way, do Cholesky factorization on it. And the other algorithm trend is doing the style low rank compression using HICMA. And what we see here is looking at the red arrows are the speedups from hardware, but same algorithm, all right? So we use different hardware, but the same algorithm. The green arrows give us the speedup from the algorithm on the same hardware, okay? And you can see we have close to 2 orders of magnitude by moving from dense to tile low rank format. And the blue arrow are basically when you combine both. This is the speed up you get when you combine both, more than 2 orders of magnitude here in this particular example. So there is a huge gain here in exploiting the low rankness of the matrix operator. When it comes to GPU, we have to adopt a different way. We have to adopt a different design of our algorithm. When I say a different design, it's always based on BLAS, okay? And this gives us really the performance portability. Because the GPU is more hardware-oriented to our throughput, we need to increase our occupancy. And because of the ranks that we get on those blocks are rather small, we don't saturate, or we don't saturate the GPU. We are not able to use all the processing or the CUDA cores from the GPU. And to overwhelm the GPU, we need to come up with this batch BLAS operation. And this is what we do in KBLAS, where we try to submit a batch of BLAS. Each of those batch contain small operation that call BLAS routines, and we try to overwhelm the GPU with that, okay? This is how we reduce the idleness from CUDA cores and increase our occupancy. And by doing that, we are able with tile low rank Cholesky to give a huge performance improvement on compared to MAGMA, where MAGMA does the dense Cholesky, and even compared to HICMA on the CPU. There is a 7x performance speedup here. This is on a Pascal P100 GPU, rather old GPU. We should run it on the latest hardware, GPU hardware. But this tells you already the trend here that we are after. So by redesigning the algorithm, but still relying on BLAS and exploiting the low rankness of the matrix, we are able to get a huge performance boost compared to Intel technology on NVIDIA processor. Okay, so that's the story when it comes to tile low rank. Okay, so tile low rank is a way to approximate, your matrix while making sure at the end you reach the proper accuracy required by the application. Another way to approximate your matrix is to use mixed precision. So we're dealing with covariance matrices. Covariance matrices basically record the interaction between various elements of your problem. And the farther you are from your diagonal of your matrix, the lower, basically the lower information your tile contain. That just goes with, covariance matrices. This is how they are designed, right? So, after proper ordering, of course, you would have those, let's say particles or galaxies or atoms or electrons interacting each other with, having a high interaction when they are next to each other. But when they are further from each other, then this is where, low rank basically, call appear. And if you do the proper reordering, all those low interaction will occur farther from the diagonal tile. So the idea is rather simple. I want to do now Cholesky on the dense matrix, but I want to operate full precision on the diagonal, perhaps a bit lower precision as I move away, and even lower precision as I am close to the bottom left corner. Okay, the idea is simple, but in terms of software and implementation, this poses lots of challenges. Okay, and those challenges today we solve them by really relying on dynamic runtime system. Okay, so the runtime system not only here schedule those tasks, but also after feeding him with the proper mapping function to tell or to give him the insight on what are the tiles that needs to be processed with lower precision, he's able not only to compute, orchestrate the data dependencies, but also change on the fly the precision of the tile that the task is about to operate on, depending on its ij coordinate on the overall matrix. And if you do that, you can get huge performance boost, right? So we looked at Shaheen here, 4,000 node, and we run this Cholesky factorization for this computational statistic application. If you were to run on this matrix size in double precision on 4K, so it's 2/3 of Shaheen, you will get 3 petaflop. If you run it all in single precision, you will get about 6.5, petaflop. But we know in single precision, we are not able to get the proper accuracy, okay, of the application. We need to have this proper, mixed precision here. So we do basically 10% in double and everything else in single precision. By doing that, we are able to satisfy the accuracy requirement of the application, and we are also getting around 5, petaflop on the system, okay? While before we were only able to get 3, because we have to run in double precision. But if you do mixed precision, you are able to get the accuracy required by the application at the level, while still performing, mixed precision computation. This is on Shaheen. We also run on Hawk on the system in Germany, in Stuttgart. So it's an AMD EPIC node. We do the same experiment, and again, we are able to run at a very 4.5 teraflop here on 1500 node of Hawk, and getting the accuracy, the right accuracy for the application. And this gives us a rather huge performance increase if you were to compare or to run in double precision. All right, so this is Hawk, right? And we run on Shaheen and Hawk are pure CPU systems, right? So, and as such, they only support double and single precision. We took it to Summit, okay? We then took it to Summit with only on 128 node of Summit, and we run on this matrix size. So Summit is IBM plus 6 V100 nodes. So we have per node 6 V100 GPUs. And what we can see here, if you were to run in double precision, we'll get roughly 3.5 teraflop. But if you run in 3 precision, because now we can do half precision thanks to NVIDIA hardware support, you can get close to 9 petaflop, right? So 9 petaflop only out of 128 nodes. So this is tremendous gain in terms of performance. But here we are really customized, right? I mean, those various mixed precision, we are of course making sure we are computing fast, but not only computing fast, we want to make sure we also reach the right accuracy of the application. And that accuracy is able to give us, that configuration of mixed precision is able to give us that accuracy. And if we did not have that mixed precision algorithm and hardware support from NVIDIA, we would be stuck with double precision, or single precision, or actually double precision accuracy, okay, for this particular application. So there is a huge gain here by applying mixed precision. Yet another chart which gives us a bit of the hardware evolution here. So this is flops against matrix size again for, again, this mixed precision maximum likelihood estimation. We are looking at 3 generations of NVIDIA GPU, P100, V100, and A100, all right? And then for the V100 and A100, this is where NVIDIA provided the proper hardware support for mixed precision. And then we were able to get a huge performance boost, right? So again, the red arrow gives us a speed up from hardware, but same algorithm. The green arrow gives us the speed up from the algorithm, but on the same hardware. And if you combine both, you get this basically huge performance improvement between running on P100 that support only double precision. And that support double precision and single precision, but we had to run double precision to satisfy the application accuracy. To A100 that provide mixed precision with hardware support in half and give us the same accuracy level for the application requirement, and this 10x, an order of magnitude performance speed up. This is out of a single card, right? Out of a single card, we are able to get 32 teraflop. This is roughly 30 node of Shaheen. Okay, so this is really impressive, right? This is really impressive, and we are really excited about it. Okay, I'm really running out of time. Let me go fast on this. So HPC software garage that we provide at ECRC, we have several software, and all of those are available online. We have KSVD to perform compression, KBLAS to extract performance out of the hardware. Those two have been integrated into Cray, Lib scientific library, and NVIDIA cuBLAS. Actually, some of our alumni went to NVIDIA, so this was a great for us recognition of the work we do in our lab. Also, I'd like to spend a few minutes left that I have here on some of the work we do in astronomy, okay? Some of the work we do in astronomy. I mostly talked about, computational statistics approach for climate and weather forecasting application. I'd like to spend the last few minutes in astronomy, computational astronomy application. We're really happy and excited to say that we support the three major worldwide ground-based astronomy effort. The European Extremely Large Telescope from an European consortium, Subaru Telescope from Japanese astronomers, and the Very Large Telescope from a worldwide also consortium. So the ELT is still being designed, okay? It's not deployed yet. But the Subaru and the VLT are being deployed. Today you have those telescopes out there, and they are trying to record, get the light from remote stars and identify those habitable exoplanets. And what are those telescopes doing? Basically, they try to outsmart the atmospheric turbulence. Atmosphere is great for humans, not so great for astronomers, because it basically distorts the light that comes in from remote stars. And then, since the light is distorted and blurred, the astronomers are not able to properly capture and identify those remote stars, all right? So I'm gonna skip on the technology they use there. It's called adaptive optics. But this is how in one chart it works. So the light comes in, and that light is being distorted by the atmosphere, and you have those wavefront sensors that capture that distorted light. That light comes into this deformable mirror. It's a deformable mirror because it tries to compensate for those turbulence that the atmosphere is behind it. So once he detects that distorted light, he ships it internally into their workload, into those high resolution camera, and then try to, in real time, try to compensate it. So in real time, in the sense that as soon as the light comes in, you really want to deform that tiny mirror to compensate right away, the effect of the turbulence, okay? So there is a component which is hard real time, and there is also a component under the hood that is soft real time. It does not need to be done or to be calculated or simulated, at a high frequency, but it needs to be performed at, during several iterations. And this hard and soft real time, we are providing, the proper linear algebra operation to support those two different workloads, the hard again and the soft real time. And I'll be discussing them, now briefly. So this is the impact of AO. On the left side, if you don't do adaptive optics, your light is blurred, and you're not able to capture the proper, the high precision, galaxy that you try to identify. If you do AO, then you are able to capture things properly. So this is the moon here, taken as an example. So European Extremely Large Telescope is one of the highest challenge for ground-based astronomy, and it's challenging because it has a huge diameter. Okay, and huge diameter means that you need to be able to scale up your your workload, your simulation, to be up to the challenge of hard and soft real time. So this is the biggest eye on the sky, this EELT. To give you the proper aspect ratio, you can see small cars here and truck, and this tells you how big is this this telescope. We put side by side with those pyramid. Again, this tells you how big again it is. It has a height of 100 meters, the largest height ever that of the telescope that will be built. Let me the computation we are able to provide here for the soft real-time processing. Yet again, they require Cholesky factorization. And what we have done is we try to do mixed precision to increase the performance of that tomographic reconstructor that relies on this Cholesky factorization. And we report flops against matrix size, so the higher the better. And here again, we do the a breakdown in terms of performance obtained by various NVIDIA GPU generation. And we can see we can get up to 3x speed up here, mixing single precision and half precision. and while still satisfying the accuracy, ultimately satisfying the accuracy of the application. The Subaru Telescope, all right. So we talked about the extremely large European extremely large telescope that is being designed at this time, right? But the Subaru Telescope is available out there, okay? Is out there, and we are actually running some of our software, in that telescope located at 14,000 feet. They have a GPU rack, a small, GPU rack hosted in their tiny data center on the telescope, and they cannot afford to have huge data center. They're limited in terms of power, right? In terms of power, to cool and to run the system. So they have only limited power envelope, and GPU for them turns out to be the way to go. And this is their existing system. We're able to port our software there, this is what we've done for them for the soft real time. We provided an SVD, a fast SVD, computation for doing the pseudo inverse. And so here we show time to solution. So the lower the better. We run on 4 V100 GPUs, and we are able to get almost 5 to 6x performance speed up compared to MAGMA implementation of this SVD algorithm. And this runs on the telescope, right? It uses real observational data set, and it shows effectiveness and is able not only to compute fast, but also to produce the right accuracy. Ouch. Ooh, okay. I guess I did not scale properly that slide, but we can still see what's going on here. I'll explain briefly. So I'm reporting bandwidth now, right? So I'm looking at bandwidth various against various matrix size, and each of those matrix size correspond to a given instrument that we're trying to deploy, or that astronomers are trying to deploy on those telescopes. The operation here is this matrix vector multiplication, which is the hard real time. Okay, so the hard real time is we compute a control command matrix that tells how those mirrors, those deformable mirror, needs to tilt in a certain way to compensate for the turbulence coming from the atmosphere. And they need to do this at high frequency. They need to do this matrix vector multiplication at high frequency. So it's important for astronomers to have that MVM operation run at high speed, at least try to be at the same pace than those wavefront sensors camera that are able to give the turbulence atmosphere. So we're looking at bandwidth, and higher is better. I guess the the blue bars from Intel are cut, but that's okay. I mean, it's slow anyway. So then we look at the other performance we got from NVIDIA 800, and also we look at NEC SX Aurora. Okay, so it turns out for small matrix sizes, when we do those matrix vector operation for in particular for the Subaru Telescope, the XXAO instrument, NEC is rather able to capture a good performance, a good bandwidth. And as we increase the matrix sizes for other instruments, we are able, NVIDIA is able to catch up and deliver, the power of HBM2. NEC SX also have HBM2 there, but the 840 gig is able to surpass or beat basically NEC for larger matrix sizes. Okay, so all of this, we're trying to package it within this MOO software. We have not released some of the code here, in particular the mixed precision. This is still work in progress. The graph that I showed earlier about bandwidth is right there. I apologize again that the graph was not scaled. So it's really exciting for us. I mean, here in this region where we try to add a new chapter for astronomy, and we're trying to bring it home. Okay, that's all. I'll be happy to take any question at this time. I hope I didn't went too much over time, and I'm here. Thank you.
Thank you very much, Hatem. Fantastic. And you can hear the digital applauses somewhere. So I ask for anyone if they have questions to put it in Q&As. And we have a first question. Can you please comment on the loss of precision when comparing the two approximation, low rank approximation, algorithm oriented, and the hardware one with mixed precision? Which one results in better accuracy or more accuracy loss?
All right, so it's a very good question because it also reminds me of one aspect that I have not mentioned, and I will say it shortly. So going back to the question, the low rank approximation. So approximation, you can do low rank, right? So it's mostly numerical approach where you try to retain the most significant information of your matrix for a given application. I want to emphasize on the given application because you would use different accuracy depending on your application, basically. So low rank give you the flexibility here. Okay, you can really approximate to the level of approximation you want, as long as at the end you are able to deliver the accuracy requirement for your application. So you do have flexibility on the software side. On the hardware side, if you use hardware, I mean NVIDIA, tensor cores or half precision or of bfloat, those various format for performing low precision matrix multiplication, you don't have much flexibility there in the sense that you have one precision, right? So you'll be at the level of half precision or the level of 16-bit half precision or bfloat, or so in that sense you do not get that flexibility. However, I mean, we try to use within the low rank approximation the kernel that NVIDIA developed for their hardware, so that we can even more increase our performance. So the accuracy, I mean, it's a bit apple to oranges to compare the accuracy that you would get out of NVIDIA hardware against the accuracy that you would get with low rank approximation. Certainly, low rank approximation give you this flexibility, and depending on the application you are supporting. But NVIDIA technology is there to be used, to be leveraged within an application, and it gives you a constant accuracy there, right? So it's one accuracy, and it's up to the application then to leverage that. The point that I wanted to mention is, because here I showed those two approaches for approximation as two swim lanes. Either you do low rank or you do mixed precision, right? But actually you could do both, right? And that's actually our future work that that we'd like to look at, where we use low rank, and we also try to incorporate NVIDIA mixed precision hardware technology to further improve on the performance. Okay. Not only we want to look at performance, but also we want to study the possibly accuracy loss there, if any.
Fantastic, thank you very much.
I
have a go ahead, Bilal.
Okay, thank you. So thank you, Hatem, for this nice presentation. So like for the many people who are developing codes, so how, and you clearly demonstrated that you can take advantage of the mixed precision. What are the guidance that you would like to share, like for people who are don't know code that are developing? So what are the best practice to do so they can develop mixed precision and eventually to take advantage of the different architecture?
Yeah, thank you, Bilal. That's a nice question. So let me apologize. Let me go back quickly to one of the slides that I mentioned about algorithm trend and hardware trends. I think this is this will answer partially the question. How to take advantage of mixed precision, right? So domain scientists actually do not look. So, at least those that we work with, we're not looking into it, right? So they just run that precision. Double precision. If I take as an example, the work that we've done with astronomers, they start with double precision. When we started working with them, it was double precision all the way, right? So it's only when NVIDIA started looking at started, where when the V100 came into the to the picture, where performance could be increased by those fast matrix multiplication, that we started looking into, hey, why not us, right? We do double precision, we want also to see if we could leverage that, right? But then when we dropped the precision to single, we've seen that we lost some accuracy, right? So, but then by performing this fine-grained computation and cherry pick which tile in my matrix I need to lower the precision, this is how we were still able to maintain the accuracy at the end. But going back to your question, I think there are some work that I'm aware of from Jim Demel group, where in Berkeley lab, where they try to see how they could help application developer to identify in their algorithm where lowering precision could have a performance impact while still maintaining accuracy. But doing this from a compiler perspective, doing this from more sort of agnostic way, right? So this would happen under the hood, and they have ways, I guess, techniques to identify such cases. So this is still work in progress. But I would say, I would go back to my first, or the main message that I wanted to convey in that slide, matricization, right? So, if you could matricize your problem, right? If you could really rely on those BLAST routine, and you could really leverage the technology brought by NVIDIA, for their GPU, but also AMD and other Fugaku and other Fujitsu, and other vendors to basically leverage the performance. So, and this would come really at sort of low cost in terms of development, right? For us to take our existing code from P100 to V100 to A100 was not, there were some challenges for sure, but the challenges were in areas of our expertise. We're not in areas where we had to implement new low-level CUDA kernel, for instance, because already our algorithm rely on cuBLAS library, and NVIDIA would not dare to put any new hardware out there without a close to theoretical peak performance cuBLAS library, right? So it will just come for free. And in that sense, I think by taking that algorithm trend where we try to matricize as much as possible our problem, I think we are hopefully on the right side of history.
Thank you, Hatem.
Another question from my side, if you don't mind. We've seen several applications, right? And obviously those are typical scientific applications that we appreciate the contributions to that. But as you know now, there is more hype and more interest on specific applications, namely machine learning and deep learning. So is there any SVD or Cholesky or some algorithm that can help on that area?
Yes. There are plenty actually, Saber. Yeah, so we are collaborating with few faculty at KAUST here and try to identify where we could do this. And this is still work in progress, and we're looking forward to it. Yeah.
Fantastic. Thank you so much. Any other questions from the audience before we wrap up? All right. If not, then thank you again, Hatem. Thank you very much for the outstanding keynote. And we look forward to have you on the eighth edition of the workshop and in future event with us. Thank you. Have a good one.
Thank you. Bye.